Now, finding G by using your smartphone, uh, it's a it's trivial in the sense that what is the simplest way of finding G by using your smartphone? Of course, I mean, you can say that, okay, I'll do this. I'll start a voice recorder and go to a silent room. And then I say something, start, and just drop the phone. And then someone, maybe my friend, will catch the phone. And when he catches it, I mean, he will also make a sound. And just by looking at the recorded sound, the difference of the two instances, I will be able to find out how much time it took for the phone to drop. And if I know the distance, then finding G from that half gt square is equal to distance traveled is trivial. Yeah, it is that simple actually. Okay. Then you might also say that the phone has an accelerometer and it shows G. So I don't have to do anything, just open that app and look at that data, and then I should be able to find G, as simple as that. Yeah, that too works. Okay, no doubt about that. But what we are going to do is a bit more complicated way of doing things, but then I just hope that it would be fun. We are planning to use one of the app that we can easily install in our Android phones, and I just hope that there are iPhone versions also for Firefox. I'm sure there will be. And Firefox is basically, it connects to the sensor of your phone, and your phone, typically the smartphone, have multiple sensors. The most important is it has a accelerometer, then it has a light sensor, and it has access to GPS, and it can, in many cases, it has a tiny compass-like gadget, which basically is a magnetometer. It can record the magnetic field fairly accurately. So using these, we can do very interesting experiments. Okay. And as far as acoustic goes, I mean, you can produce sound waves, or you can record sound waves. You can analyze the sound wave, get the frequency of a sound wave using this audio spectrum, and then you can find out the change in frequency as the phone moves or source moves using the Doppler effect. And other, I mean, like this frequency history and all. There are so many options, and some of the good physics experiment can be done. Firefox has lots of videos in YouTube where you get to know, I mean, exactly how to do things. So installing Firefox is trivial, of course, I mean, and we will use only this Doppler effect thing. So for other experiments, of course, we need to check the YouTube. But for this one, let this be our reference point, this clause. So we'll use Doppler effect, and using Doppler effect, we'll find out the G, the acceleration due to gravity. What we need is basically, we need a pendulum. Plan is that in the pendulum, the bob will be the smartphone. We'll put the smartphone here, and we will oscillate it. So simply it will go this way or that way. And then sidewise, we'll put a laptop or another smartphone. This purpose of this laptop would be twofold. It would be to control the smartphone. I mean, I am using the term laptop so that there is no ambiguity. The smartphone is the bob of the pendulum, which is oscillating, and the laptop has two purposes. The purpose one, it produces sound of a particular frequency. And if the smartphone is not oscillating, it is static, then you know the static source, that is laptop, and static observer, that is smartphone. The smartphone will record the sound, and if it records the frequency, it will find the frequency is exactly same as what is emitted by laptop. So if the laptop sound frequency is new, it will detect new, no issues there. But if it oscillates, then of course, sometimes it's approaching the source, sometimes it is moving away from the source. So depending on the sign of the velocity, positive or negative, where VR is only speed, the observed frequency of the sound as observed by the smartphone, that will have a different frequency than the emitted value. And you know that, I mean, the Doppler effect you have, I think, used before. You should be familiar with the Doppler effect. It's +2 concept. And then in the physics lab, we used to have a Doppler effect based experiment, and it is not there any longer. But anyway, it's not a new concept to you. So the new frequency or perceived frequency is basically scaled by the original frequency, scaled by this factor. The plus minus does not have to be plus minus. If you assume that VR could be positive or negative, then you need only plus or minus. And usually plus. The plus sign is for when VR is approaching the laptop. And then assuming VR could be positive or negative, it could be just 1 plus VR by V naught. That is what is given in most of the textbooks. Now, suppose smartphone records the frequency. Then, from this frequency data, it can find out VR. VR is the speed of the phone. So if you know the speed of the phone, that means you find out the speed of the pendulum, essentially. The phone is undergoing oscillation. So we would expect its position is oscillating. If the smartphone has, I mean, if the pendulum bob, its position is oscillating, then the first derivative of the position, that is velocity, that will also be oscillating. So that means you eventually get this data, then oscillating velocity of the smartphone. Once you get that, you can do many interesting stuff. For example, you can find out the frequency, and then if you found out the frequency of the pendulum, then finding G is trivial. All you need is the length. So this is the plan. This is what we plan to do. And as I said, you need a pendulum. I set it up this way. I took a small box and then made 4 holes, 4 corners, put some threads there. And this scissor, I put it on the top just to show you that it oscillates along the direction of the scissor. Okay, so left and right with respect to you. As you look at the screen, it is left to right, right to left. It oscillates. And of course, I mean, in place of the scissor, I'll put my smartphone there. Okay, and then we will control everything using the Firefox app. So what we do is the following. First of all, we need to make a list of equipment. Now, major equipment is 2. We need a smartphone, which acts as receiver, and it is the bob of a pendulum. And we need a laptop or another smartphone. That would be source. It will produce sound. And this source is static in this case. And of course, another purpose is the laptop will control the Firefox app of the smartphone. So we need to control the Firefox of the smartphone remotely. I'll show you how. So first you basically open Firefox and then you click on the Doppler effect. I showed you the Firefox menu. So when you open it, you can get the data from the raw sensor, acceleration or gyroscope or light, location, magnetometer. The pressure is, you see, grayed out in my mobile because my mobile does not have a barometer. Some of you might have a barometer in your mobile. In that case, you would be able to see the pressure data right in your mobile. But anyway, what is important for us is in the acoustic section, we need to click on the Doppler effect. Once we do that, a menu comes up which says, okay, you set the base frequency and then you set a frequency range, you set a time step, and you provide the speed of sound. So what is happening is this: base frequency is a frequency that phone expects that the laptop is producing. Okay, so it is basically the frequency of the source. The source is producing a monotonic sound. I mean, monochromatic would be better. So one frequency, single frequency, a PF tone. Let's suppose it is at 1000 hertz. Then you need to tell the smartphone that I am producing sound at 1000 hertz, and you look for fluctuation or difference of the frequency close to 1000 hertz. Now, this detection is what you call, I mean, you will learn more detail about this kind of detection. It is called a quadrature detection. Okay. Now, quadrature is slightly advanced concept. Roughly what we do is, suppose we are getting a frequency which is, let's say, 1002 hertz, 1002. And we produce a frequency, we produce a sinusoid at 1000 hertz. And then, after we record the data, after we record the sound wave of 1002 hertz, we multiply that particular sinusoid by our own generated sound sinusoid, which is oscillating at 1000 hertz. So you know what happens when you multiply two cosine functions, cosine A and cosine B. The product is cosine A plus B by 2 and cosine A minus B by 2. In this case, A and B will have different frequency. One will have 1000, which we are producing. We are at the smartphone. And 1002 is what we are receiving actually. And 1000 is our produced signal, what Firefox produces actually. So the final result would be 1000 plus 1002. That will give us 2002 divided by 2. That will be 1001. Very high frequency. The other one is the difference. That will be exactly 1 hertz. I mean, like 1002 minus 1000 divided by 2. Now, after taking the product of the two sinusoid, you will have a high frequency component, a close to 1000 hertz, and you have a very low frequency component, 1 or 2 hertz. Then what you do is you pass the entire thing through a low pass filter. That frequency range that you see, this 10 hertz, it is basically low pass up to what? So that means it will allow everything below 10 hertz to pass, and above 10 hertz gets blocked. So that means the output will be only 1 or 2 hertz. And of course, you have to multiply with the correct scaling factor and all. So this is how we detect small difference in frequency. And the method is called quadrature. This is the reason that we have two parameters here. One is the base frequency. This is the sinusoid which gets multiplied. And this frequency range is basically the low pass filter which stops the high frequency, and we get to see the all frequencies lower than 10 hertz. Typically, that is how it works. The time step is essentially that how frequently we look at the data. A sound is basically analog data continuously coming to the smartphone. But of course, I mean, we don't record it that way. I mean, we take a snapshot of the sound. So we record at a particular time some amplitude, at another time another amplitude, another time another amplitude. So we have series of times, each time one amplitude of the sound. That is how we record it. That time step essentially, you are telling the smartphone that 50 millisecond, every 50 millisecond record one data point, like that. And speed of sound, it's a standard speed of sound in air, 340 meter per second. But then if you decide to do this experiment, not in air, suppose you put the pendulum inside a special chamber where you have some other gas, let's say helium, then of course speed of sound will be different. So at least we have the option of setting it to some value. You don't have to change it. So you fire up this particular app, set the values, and then you keep it on the setting. on the pendulum, you just let it rest. And then next thing, I mean, okay. Before that, one more thing, of course. Before you keep the smartphone on the pendulum, you need to find out a way to control the smartphone. So what you do is you click on these three dots at the top, and that gives you experiment info, exporting data, sharing screenshot, or it's a timed run that you would like to start the run after 5 minutes. Meaning, typically when you press this button, it starts recording data, this play button. But you can have a timed run. And then most important for us, you can allow remote access. So I click on remote access, it gives me a security warning. Of course, I mean, you are allowing some other device to control your Firefox. So, of course, you accept that and it's okay. I mean, we are doing everything at home, so things are fine. Now, is there any catch here? I mean, what is the best way to do it? And you see, once you allow remote access, then in principle, people from outside can control your phone if they know how to do it. So how to prevent that? One way of doing this is if your laptop and mobile both connected to a home Wi-Fi router, then what happens? I mean, like the phone gets an IP address from the Wi-Fi router, which is typically an internal IP address like 192.168.0.104. This is my home IP. Okay, I mean the smartphone IP, and it got this from the home router. The laptop should also be connected to that. Now, if you say I don't have a router at home, I use mobile data, then what should I do? What you should do is, before you start this, you can switch off your mobile data access. So you are not connected to internet, and then start a hotspot using your smartphone. If you start your, you can do that, and then connect your laptop to that hotspot. If you do that, then everything, the laptop and the smartphone, they are all part of a local network that you are controlling, and no outsiders can come in that way. So one security tips that you need to keep in mind. Now suppose we did all that. We click OK, and it says remote access enabled. You can access this experiment from the following URL, http 192.168.0.104, and the 8080 is the port. So the port and IP usually they are separated by colon. So this is where you can access it. Now what do? Well, you visit that IP address from your laptop. Now the screenshot was taken one day, and this screenshot on a different day, so the IP looks different, but don't worry about it. I mean, typically that IP you should put in the browser, and if you click and you are connected to same network, then you see this Firefox window. What you see here, the same window is now visible on your laptop. Okay, and so if you click on the play, then smartphone will start collecting the data. That is how it works. So you can control your smartphone. Now at this stage, your laptop is connected, smartphone is ready, and it is sitting on the pendulum. Maybe you can start oscillating the pendulum. So if you oscillate the pendulum, it takes like 1 or 2 minutes for oscillation to settle down. What do I mean by settling down? Typically, you see, if you start an oscillation, initially you may notice the oscillation is not very smooth. I mean, it's not just a one direction left to right. It might be a little jittery. It's twisting a little. The cables are twisting a bit. Usually, such motions, they die down faster. They die out faster, and in a couple of minutes, 1, 2, 3 minutes, the only motion which will remain is the motion along this scissor. That will remain, and then there will be a nice motion set up. And I'll try to show you a video, but that comes later. First, let me go through the operations. So, smartphone is oscillating. It is ready to acquire data. And then, in the laptop, you have already connected. You are ready to press this key. But before that, your laptop must generate some sound. I mean, how do you do that? You can simply Google search that online tone generator. Okay? If you do that, you can see that when I was doing this experiment, in the next tab it is open. Okay. Unfortunately, I did not record a screenshot, but it is there in the video. I'll show you that. So online tone generator, if you search or some kind of tone generator, there are lots of websites where you can go and it gives you option of specifying a frequency, and then you click on play, then it just plays the sound at that frequency. So what we do is we go to an online tone generator and then set the frequency 1000 and we just play it at maximum amplitude. Okay, so laptop speaker is producing sound at 1000 hertz, and this mobile is supposed to catch it. It's ready to catch. And then what you do is you start the play button and click on this results. This is the setup window. If you go to the results window, you will see it will trace out the registered frequency in the laptop and also in the smartphone. You see, laptop is capturing the smartphone screen. I mean, not capturing, it's showing you the Firefox screen. And in the mobile, Firefox is also open, right? I mean, that is where you allow the remote access. So you will see in real time that there are tiny oscillations, many. And then this window, the x-axis automatically gets adjusted to accommodate all the oscillation that can come in, and you will see that, I mean, here I recorded for about 500 seconds. There are many oscillations took place. And what is interesting, I have a super slow frequency. You see, I mean, it's not a pure sinusoid. There is a modulation. And that modulation is like a one-time period over 500 seconds. So that means the period is 1 by 500. It's a very slow frequency. Could be something to do with the setup, but we can ignore that. Why we can ignore that? Simply because all we are interested in is this high frequency periodicity. So we do not need to know, I mean, like what the slow one is. Maybe at some later stage, we will investigate that, but not today. Now, what you see is the frequency that I could record, about 1000 hertz. What is happening here? I mean, let me look at the data and then try to tell you the situation. The smartphone is oscillating, fine, and the laptop is producing a sound at 1000 hertz. And smartphone is catching the signal, and it does not get 1000 hertz. It gets a signal which is oscillating between 999 and 1001. And you see it's so precise that less than 1 hertz, and our smartphone can detect that, can resolve that quite well. I mean, it's very impressive that way. So this is how many data points are getting recorded. And the smartphone itself calculates from the frequency data the speed, and it tells us the speed is like in this scale, which is like minus 0.5 meter per second, which is 50 centimeter per second. This way or that way. So our typical values are like 20-25 centimeter per second. That is perfectly reasonable. I mean, the pendulum that I had was slightly, I think it was very close to 1.8 meter, almost 2 meter, almost 2 meter. So for a 2 meter pendulum, and I try to use small oscillation. And this velocity is quite reasonable, couple of centimeter per second, okay, tens of centimeter per second. So it recorded that, and then what? Then it's fairly simple. The easiest way of finding out time period is, I mean, like just zoom up the data and then count in a given time how many periods are there. 1, 2, 3, 4, 5, 6, 7, 8, 9 in about like 20 seconds. That gives you some idea. If you need better than that, then of course it is a bit painstaking to count for like 100 seconds or so. But still, it is doable. It's doable. You can do that and find out how many periods are there in a given time, and you can find out the period. Okay. Of course, I mean, if you say, no, I would like to do something a little more advanced, I mean, I'm not happy with this, I mean, I need more precise value, then you export data. You export data, and then you Fourier transform it. Okay. You Fourier transform it. So what you see here is basically a small program that I have written, and I'll show you, of course. What it does is, here is the data that I have recorded, and I took the Fourier transform of the data. So Fourier transform essentially finds out that how fast the data is oscillating and which frequency has how much intensity. So for example, I have a data which is like a beat pattern in the sense, say for example, I'll give you an example, like a cosine omega t. This is one of my data. As a function of time, I am recording a cosine omega t. And then not just that, I am basically recording a cosine omega t plus a sine omega prime t. So if I have two different frequency, omega and omega prime, present in the data, then their sum, if omega and omega prime are close, then it looks like a beat pattern. You have seen that, particularly you have seen the example of it in the coupled pendulum experiment in the first year, where the beat pattern is basically coming from the difference of the frequency. So suppose something similar you have, and suppose you take the Fourier transform of the data. What do you get? Well, you get two peaks. The peak one will be at omega, and intensity would be proportional to a square. And second peak would be at omega prime. Intensity will be proportional to a square. I mean, I have taken both a. What about a cos omega t plus b sine omega t kind of thing? Then of course, yes, you get one peak at omega, the other at omega prime. Intensity will be proportional to a square and b square. No, it's that simple. So that means if you have an arbitrary waveform, lots of frequencies and etc., if you take the Fourier transform, it will tell you how much, which frequencies are there, and to what extent, what is the amplitude of that frequency, that sinusoid containing that frequency. So what I did is, I did that, and what I found is, I found the frequency, of course, and I got some higher harmonics. Okay, I mean, this is the fundamental, then the next one, then next one, they have a lower amplitude. I need to analyze whether this is coming from an artifact of recording the data. You see, the smartphone microphone is not a perfect microphone. I mean, it can distort the sound, and similarly the laptop, the frequency that it is, when you say that to your laptop that you produce a sound at 1000 hertz, what if it is producing 2000 hertz also, because the speaker size is finite, and yeah, that part yet to be analyzed. So that I do not know yet, but then we don't need to know that much, simply because the fundamental is good enough for us to observe. From there, what we see here is at this particular frequency, I mean, this oscillation is happening at this frequency. Okay, we ignore the intensity data, except that we note that this is the largest peak that we have. It's fine. And then if we know the frequency, from there finding out G is just one step. We know the frequency of oscillation very precisely now. Now, I would like to show you the video which is I put it in the presentation, but then it's not behaving very well. So maybe I'll put it this way. Okay, wait a minute. I need to share my screen instead. So I'll change the presentation. I'll stop this presentation and I will switch to another one. Basically, I'll show my screen. Okay. Now, okay, I got very interesting comments. Okay, what Aditya says, drop it and see how long it takes to fall. Of course, yeah, very nice. Yeah, if you are, that rich that you can afford to break smartphone for measuring G, okay, please, I seriously need your contact. And then, shouldn't there be damping? Yeah, of course, there is damping. I mean, you can see that damping. You see the amplitude of the oscillation is becoming small, right? That is basically the damping. If you ignore this frequency modulation, then overall the wave is getting smaller, and I don't have more data. Once I record it for 1,000 seconds, and I could show you that actually the amplitude is reducing. If you do okay, no, that comes later. Phase plot kind of things comes later, but we will discuss that. But anyway, what I need to do now, sequentially, I stop this presentation, and I would like to share another window, which is the video, and I share it. Can you see this one? I guess you can. Please write yes. Wake up and write yes in the chat window. Then I know
yes,
that.
sir.
Okay, great. So I am playing this. So here, what you see in my laptop is the online tone generator. Okay, I'm sorry. Yeah, here it is, the online tone generator. And you can see, I have written like 1,000 hertz, 2,000 hertz. This is for testing. And this bar was like controlling the frequency or amplitude, I forgot. And then eventually you click on play and it starts playing a sound at that frequency. Simple. And then in the next tab, here is the phyphox. I can see the phyphox of my mobile, and I started playing. I clicked on play, so phyphox data is getting recorded, and I can see the frequency and speed in my laptop, and they are oscillating. It's not nice sinusoid, but it will do. I can live with that. All I am interested in is the periodicity. I do not expect this crude setup to give me very fine data. Now, you see in the real time, the mobile phone window is getting updated, more data are coming in, and the frequency and velocity, they are going up and down, nice sinusoid. And basically you have to do it for 500 seconds. So yeah, okay. Now, what is the problem? What is the problem of playing it? This is basically the video is running on a loop. So while I talk, you get to see this video again and again. And of course, I muted it. Otherwise, the screen would be flooded with this 2,000 hertz sound. Anyway, now what is happening is this: when you record this, it is better not to have anything moving nearby. So which means it should be quiet. If dogs are barking outside, or if a vehicle is passing by, or your friends or your parents, they are shouting at you, then all this distorts the sinusoid that is getting recorded. Okay. And one time I moved my hand, even that produced some discernible signal. So it's better to be, in a quiet room and do it. So that is one thing that you have to kind of ensure. Okay. Now I stop sharing again and I switch back to the presentation. So here I am, and I did all that. analysis using Fourier Transform. And what happened? Okay. Is this the only method? No, definitely not. There are other methods. Okay, there are other methods. If you have the accelerometer in your Firefox and you switch it on, then you will see that it records the acceleration. Just the way you recorded the frequency, you can record acceleration, and for that you don't need another smartphone, you don't need another laptop, you don't need another anything. You just need your phone. So suppose you keep the pendulum, put the phone there, and start the oscillation. And if you can, control it from outside or use a timed run. Either way, you can export the accelerometer data as the phone is oscillating. So basically, you will have acceleration of the phone as a function of time. Now, a pendulum, when it oscillates, its position oscillates, velocity oscillates, acceleration also oscillates. After all, the position, you can describe it like x as a function of t is equal to some amplitude, maybe a naught cosine omega t. And then if you take its derivative, that gives you the velocity, which is minus a naught omega sine omega t. And you take the derivative again, then you get the acceleration, which is again a sinusoid. So if you can record that acceleration data, then you can do a numerical integration, and then that will give you kind of velocity. Integrate once more, you get position. So if you plot position versus velocity, what you get is a phase plot data. The phase plot, the real significance of phase plot will be apparent to you in the third year, but that does not mean that we can't plot it. Numerical integration straightforward, we can do all that. But then why I'm not encouraging at this stage is basically this course is not a programming course. If you have to write a lot of programs, that is not the purpose of this course. The purpose is to get the sensor data and do some simple mathematics and get it quickly. I mean, those of you who would like to take the plunge and would like to check how the programming this thing looks like, I mean, I'll show you the program, of course, but you don't have to do it. It is an option.